In previous sections, we defined the 6 trigonometric functions as angles in standard position or as ratios of a right triangle. Often, it is necessary to modify the trigonometric functions so that their domains consist of real numbers rather than angles. Hello, my name is Tom Atwater, and in this section, we will define the 6 trigonometric functions as circular functions with real numbers as their domain. We will begin by defining the unit circle and circular functions. The equation for a circle is, of course, x squared plus y squared equals r squared. A unit circle has its center at the origin with a radius of 1 unit. So the equation for the unit circle is x squared plus y squared equals 1. Starting at the point 1, 0, which we have right here on the x-axis, we take and wrap a real number line around the circle. And in this particular case, I am going to begin to wrap the number line around the unit circle like this. And in particular, I'm going to stop, though, at the point x, y, which is, of course, the terminal side of this angle theta in standard position. And here's my angle theta. Now, the arc length, we use the letter S to represent arc length. And of course, that is going to be measured in linear units, either centimeters, or it could be feet, it could be meters. Theta, the actual angle, though, is measured in radians. So S is in linear units, but theta is in radians. All right, so now, this leads to circular functions in the following manner. If you remember from triangle trig, let me drop a perpendicular forming a right triangle in which this side, of course, would be the value for x. This side would, of course, be the value for y. And I'm going to label this theta prime just to distinguish it between the theta that we've already drawn. From your right triangle trig, you know that we can set things up where we can take, for instance, the sine of theta prime and say that that's equal to the opposite side over the hypotenuse. And again, this is the unit circle, so the hypotenuse is equal to 1. So not only does sine of theta prime equal y over 1, but that's also the sine of theta equaling y over 1. So let's write that down. And that also equals the sine of theta. And of course, in this particular case, the sine of theta is positive in quadrant 2, and the sine of theta prime is obviously positive. So they are equal to y over 1, which of course means they are equal to plain old y. Well, now let's realize then that the sine of the angle measured in radians, sine of theta, we can relate that to the sine of the arc length s. And what we can say is that sine of s is equal to y. So let's take a look. I'm saying now the sine of the arc length s is equal to y. And by similar reasoning, which I won't take us through to the right triangle, we have that the cosine of the arc length s is equal to x. Well, now what we can do is look at the remaining trig functions based on the circular functions and define each of them. So let's take a look at the other 4 trig functions. We already know that sine s is equal to y, cosine s is equal to x, tangent of s is equal to y over x, x, of course, can't be 0. We have cosecant of s is equal to 1 over y, and of course, y can't be 0. Secant of s is equal to 1 over x not equal to 0, and cotangent of s is equal to x over y, where y is not equal to 0. These may look very familiar to you, and in fact, they should look familiar to you because we looked at right triangle trig earlier, and you will see that we use the same set of letters in defining the right triangle trig. The difference was we were taking the sine of an angle as measured, not the sine of the arc length as measured. These, the circular functions, are the sine, cosine, tangent, cosecant, secant, and cotangent of arc length measurements. Let's do an example now that we have an understanding and we can evaluate trig functions based on the angle being in radians as opposed to in degrees. Find all 6 circular function values of the real number pi over 6 by hand. That is to say, don't use a calculator. Now, from the properties of our 30, 60, 90 triangle, an angle of pi over 6 radians is equivalent to 30 degrees. So let's recall, if I were to draw a unit circle and draw pi over 6 radians. So this measure is pi over 6. But again, recalling from our triangle trig, this pi over 6 is 30 degrees. Therefore, if I were to draw a triangle here, then I know this is 1. This side over here is going to be 1/2, and this side over here is going to be the square root of 3 over 2, which means this point would be labeled square root of 3 over 2, comma, 1/2. So now, if I use my definitions that we just looked at, for instance, that the sine of this angle pi over 6, as measured in radians, would be equal to the y value. So I know sine pi over 6 is equal to 1/2. I can now find all of my other trig functions, for instance, cosine pi over 6. That's going to be equal to the x value. The x value is square root of 3 over 2, so square root of 3 over 2. The tangent of pi over 6 is equal to y over x. So I take my y value, 1/2, put that over the x value, square root of 3 over 2. The 2's can cancel each other. This is 1 over radical 3, which when we rationalize it becomes the square root of 3 over 3. So now let's finish this off by looking at the cosecant of pi over 6. Cosecant of pi over 6, remember, is 1 over y. So it's equal to 1 over the y value, remember, is 1/2. And so that's equal to 2. The secant value of pi over 6 is equal to 1 over x. So it's 1 over radical 3 over 2. So, of course, that's equal to 2 over radical 3. And in order for me to rationalize the denominator, I have to multiply top and bottom by the square root of 3 over the square root of 3. So that's going to equal 2 square roots of 3 over 3. And then finally, for my cotangent of pi over 6, that's equal to x over y. X is equal to the square root of 3 over 2, and y is equal to 1/2. I can cancel out my 2's and that leaves me with square root of 3 over 1, which of course is just the square root of 3. All right, that's how you find the 6 trig functions using the new circular definitions of, in this case, one of the special angles. One of the most important tools to have in the trigonometric solution toolbox is the unit circle showing all of the special angles, written in both degrees and radian values, and then the corresponding arc length, the S values. Let's look at the complete unit circle, and we'll use it to solve some trigonometric functions. So here's our unit circle, and you can see that the problem we just did would have been, if I were to draw this angle theta, and we said it was pi over 6, which would have been the equivalent of 30 degrees, and you can see that the point should be labeled as we had done. Now, we can look at the other points on this circle, for instance, pi over 4, which is the equivalent of 45 degrees, and here would be my x comma y value. 60 degrees is the same as pi over 3, and what I want to point out to you is the relationship between these two points. Remember that 60 degrees and 30 degrees are complementary, and that they appear in the same right triangle. And notice that the x and y values have simply been interchanged here. So they have the same actual numerical values, but the x and y's have been interchanged. What I then want you to notice is, regardless of where else you go on this unit circle, you will find those same 3 values. When I say values, those same 3 points will be throughout the rest of the unit circle. So initially you will say, my goodness, there's a whole bunch of things that I need to memorize. And the answer is no, you don't have to memorize them. In fact, if you memorize just these 3 that are in the first quadrant, and then apply the idea of the sign SIGN, that is, we know that everything is positive for the trig values in the first quadrant, but in the second quadrant, we know that sine and cosecant, are positive, and we know that tangent and, of course, cotangent are positive here, and we know that cosine and secant are positive here. Then you can calculate the remaining values for each of the angles by using the 3 that you've memorized in the first quadrant and then applying the appropriate sign, SIGN, for those trigonometric functions. Okay, now what I want to do is use the unit circle in the next example to find the 6 circular functions of the given angles. Use the unit circle to find the exact values of cosine 7 pi over 4, sine 7 pi over 4, and tangent of negative 5 pi over 3. Let's apply the circular functions to solve this particular problem. So what I want to do then is start by drawing 7 pi over 4. So that's a positive angle, and 7 pi over 4 lands me here. And actually, it's a little bit further along. Let me redraw that. It should be smack dab in the middle there. And what I know is if I would draw the unit circle on here, that this point would be square root of 2 over 2, comma, negative square root of 2 over 2. And so now, if I want the sine of 7 pi over 4, then what I'm looking for is the y value. And the y value is negative square root of 2 over 2. If I want to find the cosine of 7 pi over 4, then what I'm looking for is the x value. So cosine 7 pi over 4 equals the square root of 2 over 2. All right, the other problem that we were asked to do is to find the tangent of negative 5 pi over 3. So I need to redraw that, or draw that angle, because of course it's different than the 7 pi over 4. So for that angle, it's negative. So we go negative 5 pi over 3, and it's going to land approximately there. Negative 5 pi over 3. So therefore, if I draw my unit circle, this point is going to be labeled 1/2 comma square root of 3 over 2. And therefore, if I want to find the tangent of negative 5 pi over 3, then that's going to be equal to the y value divided by the x value. So I will take the y value, square root of 3 over 2, divide that by the x value, 1/2. I can cancel out my 2's, and of course it all equals the square root of 3. All right, now let's apply the circular functions to solve application problems. Here's our first application problem. The average number of daylight hours at San Antonio, Texas, can be modeled by the equation f of x equals 1.95 cosine of the quantity pi over 6 times x minus 6.6 plus 12.15, where x equals 1 corresponds to January 1st, and where x equals 2 corresponds to February 1st, and then so on. Evaluate f of 7 and interpret the results. So I have the equation written up here. We want to evaluate f of 7. Make sure that your calculator is in radian mode, because that's what we're dealing with here, is radians. And now what we do is substitute 7 for the x. So we have 1.95 cosine pi over 6 times 7 minus 6.6 plus 12.15. Plugging all of that into your calculator and multiplying it out, plugging it into the calculator, you'll find that f of 7 is going to be equal to 14.06. But what does that really mean, the 14.06? What it means is that we're looking at f of 7. F of 7 refers to the 7th month, in other words, July 1st. So on July 1st, there would be slightly more than 14 hours of daylight. Okay, well, now that I've done an application problem, I would like to give you the opportunity to solve an application problem using the circular functions on your own. The maximum afternoon temperature T in degrees Fahrenheit in a given city might be modeled by T equals 60 minus 30 times cosine of x pi over 6, where x represents the month, with x equaling 0 corresponding to January, and x equaling 1 to February, and so on. Find the maximum afternoon temperature for January and for April. Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. Welcome back. Let's see how you did on that problem. First thing I want to do is write down the equation that t equals 60 minus 30 times cosine of x pi over 6. We want January, which is the equivalent to x equals 0. So I plug in 0 for my x value. So I get t equals 60 minus 30 times the cosine of 0 times pi over 6. But 0 times pi over 6, of course, is 0. The cosine of 0, all right, cosine of 0 means that we want the x value when there is a angle of 0, which, of course, that's the point 1 comma 0 on the unit circle, so the cosine is equal to 1. So this is just 60 minus 30 times 1, which of course is 30. Well, what does that mean? That means that in the month of January, we're looking at 30 degrees Fahrenheit. Okay, the other half of the problem was April. Well, what does April refer to? April would in this case be x equaling 3. And so we plug in x equals 3 to the equation. So t equals 60 minus 30 times cosine 3 pi over 6, which of course reduces to pi over 2. Now, pi over 2, when you do it on the unit circle, is along the y-axis. So that point would be 0 comma 1. So the cosine of, in this case, pi over 2, the x value is 0. So therefore, t is equal to 60 minus 30 times 0, which of course then is equal to 60. And what does that mean then? It means that the maximum temperature for the month of April would be 60 degrees Fahrenheit. You did a lot of great work in today's lesson. Now, be sure that you work all of the exercises that your teacher assigns, because you'll find the problems both interesting and fun to solve. We'll see you next time.